Hello, well, welcome to the fifth lecture of this course called Behavioral Theory of Systems with view towards data driven control. So, we were looking at kernel representations of behaviors of dynamical systems which are linear and shifty invariant and described by difference or differential equations. So, just to give you a quick recap, what we found out in the last lecture was that if we have two behaviors given by two kernel representations, such that these two kernel representation matrices are related to each other through what is known as a unimodular matrix, right, where U psi is a unimodular matrix a square matrix whose determinant is a non-zero constant, then the two behaviors are equal, right. This also tells us that the same behavior can in principle be represented by two completely different kernel representation matrices, as long as they are related by a unimodular matrix like this. The two behaviors are equal, the two kernel representations are equal, the two solution sets are equal. Now, what is the meaning of this unimodular matrix multiplication? Well, so first thing, unimodular immediately implies that U psi is invertible. That means its inverse is also a polynomial matrix. This is very important for us to realize that this is different from your normal understanding of invertibility. You see, for constant matrices over real numbers, if you look at a square matrix, you call it invertible if the determinant is non-zero, right. But here determinant just being non-zero is not enough. It cannot be a polynomial, it has to be a constant. Can we have examples of unimodular matrices? Well, of course, one can easily concoct such examples, namely a 2 by 2 unimodular matrix can be like this. This is any arbitrary polynomial, this is upper triangular, you see, and its determinant is 1, which is a non-zero constant. So, therefore, this is a unimodular matrix. Yeah, and you can easily obtain its inverse, if you want to find out its inverse, it is just 1 minus p psi 0 1. I think I have not made a mistake anywhere. This is 1 minus p, yeah, this is fine. This indeed is the inverse, right. So, you see the inverse also is a polynomial matrix. If the determinant of the matrix of the square matrix was only a non-zero polynomial, but not a non-zero constant, then it will admit an inverse, but not in the ring of polynomial, in the polynomial ring, yeah, but rather it will admit an inverse over the rational functions, the ratio of polynomials. That is not good, because ratios of polynomials, as of now, we have not made sense of ratios of polynomials giving rise to differential equations, right. So, this, remember, this is I am writing it as I, but actually this is the polynomial differential operator, this DDT operator. So, that is why, what do you mean by DDT inverse? Not yet clear. You can say that, okay, this is integration and stuff, but no, you have to be careful with that. It becomes even more complicated if you say DDT plus 1 inverse. What does this even mean, right? So, therefore, we need this invertibility over polynomial rings, okay. And remember, this is a sufficient conditions, this is not necessary. I mean, the two things does not have to be equal. if the two behaviors are equal, then it does not, at least at this point, does not necessarily mean that the two kernel representations are related via unimodular matrices. I will give you an example. Think of solutions not over C infinity, but C infinity 0. What does this mean? This also is often denoted by the letter script D. This means C infinity functions with compact support. C infinity functions with compact support. That means supports given by closed and bounded sets. Yeah, such functions are called functions coming from D. Now look at this equation. Look at d dt w equal to 0, where w is a C infinity function with compact support, right? What sort of solutions do we have? D dt w equal to 0, you know that the only solution is that w is equal to a constant, right? But w being a constant identically is a compactly supported function only when k is equal to 0, right. So therefore, as far as this system is concerned, the only solution set is w is equal to 0, identically 0. That is the only solution set. So that is my behavior if I take this as my function space, right. But obviously, if we have this equation 1 times w equal to 0, then this immediately means w is identically 0. It is the only solution. Yeah, so you see, two sets of equations are giving rise to the same behavior, namely kernel of 1 and kernel of d dt. The two are equal if you are looking for solutions which are compactly supported. These two kernels are equal. But are these two matrices related by a unimodular matrix? Of course not. See, d dt, so let me write xi, yeah. So I have been using this letter, why not? I have introduced this letter already. So xi is equal to obviously xi times 1. So compare this with this is r, this is r prime, so this is my u, or rather f, correct? So f xi in this case is equal to xi, and this is certainly not unimodular. Okay. So it is only a sufficient condition, the relation by being related by a unimodular matrix giving rise to the same behavior, that is a sufficient condition, not necessary. It will become necessary if, for example, we think of only we get rid of situations like this. We do not consider situations like solutions coming from compactly supported functions. Yeah, if we allow C infinity functions, then we will see later that this is necessary and sufficient. But we will look at that in a moment's time from now. Right now, what we are interested in is this question that, okay, is there a deeper meaning to this relation by unimodular matrices? Look at the polynomial matrix R xi. Okay. What is this matrix? This matrix has G number of rows and Q number of columns. These are the entries. Okay. These are the entries. Now, the moment I multiply from the left by a square matrix, what am I essentially doing? This matrix is getting multiplied by a square matrix. Okay. What happens when I multiply this by this row? Yeah. Let me name these rows, namely this is, let's say, F0, sorry, F11, F12 dot 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 up to F1G. Okay, and let me name these rows as well. This is R1 row, this is R2, so on up to RG. The product F times R, the first row of the product is nothing but F11 R1 plus F12 R2 plus dot 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 F1G times RG. Do you agree? This is the first row of F times R, isn't it? Yeah, this is the first row. Likewise, the second row of Fr is given by F21 R1 plus F22 R2 plus dot 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 up to F2G RG, isn't it? That is how you produce all the rows. So, in fact, it turns out that every row of F xi R xi, every row of F xi R xi every row is in the is a linear combination of the rows of R. So simple, isn't it? So if we define this module scripted R as the row span of this matrix R xi, but row span over what? Row span over R xi. That means the coefficients that I am taking for the coefficients that I am taking to take these linear combinations are not real constants, but rather polynomials themselves. See, F11, F12, all these are polynomials themselves, correct? So therefore, every row in fact is just a linear combination of the rows of this matrix R, which means every row in this product belongs to the row span of this matrix. So that means every row of F xi R xi belongs to this module R. Because of this, it also follows that if I define the row span of R prime, so this is my R prime, right? This is my R prime. Every row of R prime is in the row span of R, so it's in R. So now if I define the row span of R prime over R xi, because every row of this guy, every row of R prime is an element of R, when I take linear combinations of those rows, they obviously are also linear combinations of the rows of R. Linear combinations of linear combinations are linear combinations. So therefore, this must then be a sub, this row span must be contained in this row span, correct? Yeah. If you are getting a little flustered by this idea of row span, just go back to your linear algebra classes and recall that row span. See, if you have row vectors, if you like, you have column vectors. Likewise, if you have row vectors, yeah, multiple row vectors, and you look at their linear combinations, that is what gives you row span. Right? What we are talking about here are rows of polynomials. So we have something like a R11 xi, R12 xi, dot 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 up to R1 Q xi, each of which is a polynomial. This is a polynomial row vector. So, this guy is a typical element of this set R1 cross Q xi, okay, right. This is just like a row vector of real numbers, but instead of real numbers we have polynomials now, but it is still just a row vector, right. I hope you are not being I hope you are not being too sort of flustered to make this connection. You are familiar with row vectors of numbers, this is just row vector of polynomials, right. So, both of this, so such a thing, the collection of row vectors of polynomials, collection of row vectors of numbers is a vector space. Yeah, here it is a little more than a vector space, or perhaps a little less than a vector space, a little different structure than a vector space, right. Whether you can call it richer or less rich structure than vector spaces, that is your call. Such things are different because they are defined over rings as opposed to over fields, as opposed to vector spaces which are defined over fields. Such things are called modules, okay, right. So, then R is actually a submodule of this module. So, modules roughly speaking are like vector spaces, but they are defined over rings. The scalars are coming from the rings as opposed to vector spaces where the scalars come from a field. And because rings are different from fields in the sense that fields admit multiplicative inverses of all non-zero elements of from the field, from the set. Yeah, in rings you don't get you are not guaranteed to have multiplicative inverses of all non-zero elements. There might be elements which admit inverses, but there might be elements which do not admit inverses. Think of polynomials, yeah. Non-constant polynomials, non-zero non-constant polynomials do not admit inverses. 1 by xi is not a polynomial, yeah. Likewise, one can think of integers, yeah. Integers also form a ring because integers other than +1 or -1 do not admit multiplicative inverses, okay. So, a module is like a vector space, but it is defined over a ring. So, here is one such example of a module, and R, the row span of this matrix R xi, is actually a submodule of, like we have subspaces, here we have submodule. This is a submodule of this module, okay. What we have seen here is that R prime is a further submodule of R when the relation between R and R prime is given by this. R prime xi is equal to f xi times R xi, okay. Now, you see, if f were unimodular, if R prime xi were equal to u xi times R psi, where this guy is unimodular, then obviously R prime is contained in R, but because it is unimodular, I also have R xi is equal to a polynomial matrix U inverse xi times R prime xi, right, exactly same relation. So, then following exactly the same ideas, the row span of R, every row in R is actually a linear combination of rows from R prime. So, every row in R belongs to R prime. So, the row span of R must belong to must be contained in R prime as well. So, we have R contained in R prime. So, we have both the containments, which implies R must be equal to R prime. So, you see, the crux of the matter is that if we have two behaviors given by two matrices, kernel representation matrices, if those two kernel representation matrices span the same row span, if R and R prime are equal, then that means the behaviors are equal. Yeah, being related by a unimodular matrix means the row spans are equal. That's why the modules are equal. So that's why when we have two matrices related by a unimodular matrix, it means the two row spans are equal, and that also means that the behavior is the two behaviors are equal. So R prime xi equal to U xi R xi, that is equivalent to saying R prime module is equal to R, and because this implies B equals B prime, by this equivalence this means this also implies B is equal to B prime. Okay, which should not come to you as a surprise, because after all, you see, when we are dealing with equations like Ax equal to 0, I'm sure all of you have solved equations like this, Ax equal to 0, homogeneous systems of equations where A is just a constant matrix. Ax equal to 0. I'm sure you have solved equations like this, right? Ax equal to B, the homogeneous part of that, and that is Ax equal to 0. And you know that by doing this row reduced echelon form, what we are saying is that we get an equivalent system of equations which give rise to the same solution set, isn't it? You do row operations on this guy and make it row reduced echelon form. These are the first things that you learn in your linear algebra course. And the reason that this is true is because when you do this row reduced echelon form kind of idea by doing row operations, you are obtaining equivalent sets of equations, and they are guaranteed to be equivalent because they span the same, they have the same row span. As long as two matrices have the same row span, their homogeneous solution space is also the same. Their null space is also the same. Same idea is happening here, but the interesting bit is that now we are dealing with differential equations and difference equations, as you'll see in your exercises, rather than just constant equations, but still similar ideas hold. That's the beauty of abstract systems theory. Now, so far so good, but where we go from here? As you can see that like in the case of constant matrices and obtaining row reduced echelon forms. I mean, why do we obtain row reduced echelon form? How does it help? Because row reduced echelon form has this very nice structure of being like almost like upper triangular and almost like an upper triangular matrix. You can read off the solutions from there. You can solve Ax equal to B, obtain basis vectors for solutions of Ax equal to B, rather Ax equal to 0, by looking at that matrix if A is in row reduced echelon form. We ask the question, is it possible to obtain equations in a nicer form? Now that we can do this, can we exploit this idea of multiplication by a unimodular matrix and converting to equivalent systems? Can we exploit this idea to obtain a better, more useful system of equations from a given system of equations? Yeah? Why don't we start with the example that we were looking at the beginning? What was the example? The example was as I'm going to write now. Remember, the equations were xi squared plus 3 xi plus 2, and here I have xi squared plus 4 xi plus 3, and remember this came out to be the same solution. This came out to have the same solution set as the kernel of just xi plus 1. Can we do something and get that? Yeah. Okay. Look at this guy and then look at these two polynomials and then ask ourselves this question, that given two polynomials, how can we obtain another polynomial from these two? Something that goes back to your high school days, yeah, actually comes very handy in this situation. Can't we divide one of the polynomials by another polynomial, yeah, and obtain something of lesser degree? Yeah. So, division with remainder, correct? That is Euclidean division. Can we do Euclidean division here? Let us see. So, I am going to do Euclidean division, but at the same time I am going to obtain two polynomials, yeah, a new set of polynomials. What I am going to do for that is I am going to do some row operations. I am going to encode this division algorithm through a row operation, and row operation is encoded through multiplication by a square matrix from the left. So, what sort of square matrix do I have in mind here? I am going to keep the first row intact. So, I am going to keep this as 1 0, and I am going to change the second row by the following. I am going to divide the second row by the first one, and then I will see what the remainder is. So, the second row gets multiplied by 1, and here because the two degrees are equal, I will just do 1 minus 1. So, here the division requires just subtracting the first polynomial from the second one. So, that is why I put a minus 1 here. Okay. Now, what is the result of this product? The result is the first one is going to be xi squared plus 3 xi plus 2, but then when I subtract I actually get xi plus 1, right. You see, xi square gets cancelled out, 3 xi minus 2 xi is xi, and 4 minus 3 is just 1. Okay. So, this is what I get, and then I do a little permutation. Okay. So, let me call this matrix as E1. This is of course R. So, E1 times R is this R1. Okay. I am going to multiply this further by E2. What is my E2? E2 is just a little permutation. This is E2. This multiplies R1, and that produces xi plus 1. It just permutes the two rows, and xi squared plus 3 xi plus 2. Why do I do that? Because I want my first entry to have a smaller degree than the second entry. Okay. And now I do the following. So, this is my E2. So, I keep track of what is happening. I have E2 times E1 times R equals R2. What is R2? R2 is xi plus 1 and xi squared plus 3 xi plus 2. And now I multiply this once again by another matrix. I keep the first row intact, and second row I do second row minus xi plus 2 times the first row. So, I put a minus sign here. So, this times R2, what will that be? The first will remain intact, xi plus 1, and second will be what? You see, this I know is a product of xi plus 2 and xi plus 1. So, when I multiply by xi plus 2 and subtract, I actually get 0, and this is my R3. Okay, and this is my E3. So, now let me just write it together. What do I have? I have 1 0 minus xi plus 2 1. This is E3. E2 is what? E2 is just permutation. Okay, here. What is E1? E1 was another row operation given by this. These three matrices multiplying R, which was xi squared plus 3 xi plus 2 xi, and here I have xi squared plus 4 xi plus 3, and the result, lo behold, is just this. Yeah? Now, what is this? Oh, sorry, I made a mistake here, a terrible mistake here. This is 1. If this is 1, what is the determinant? Determinant is 1. This is a permutation matrix. What is this determinant? Determinant is equal to minus 1 is equal to. What is this determinant? Determinant is equal to 1. So, what is the determinant of this product? Determinant of product is product of determinants, right. So, therefore, this determinant is also equal to minus 1. So, that means here is a matrix whose determinant is minus 1. So, this is a unimodular matrix. It is a non-zero constant that multiplies these two polynomials and gives me this. No wonder that we had the same behavior, because the two are related via a unimodular matrix, unimodular transformation. And I am sure you are not surprised to see that this xi plus 1 is nothing but the GCD of these two polynomials, and because it is the GCD, that is why it gives us the same solution set. Now, this is a very simple example, toy example, for which we could just do these calculations by hand. The question is, can we do it in general? Yeah? The answer of course is yes. And what comes in handy is what is known as this fantastic result called Aryabhatta-Bezu identity. Aryabhatta-Bezu identity. Using Aryabhatta-Bezu identity, we can obtain this nice, more useful representations by doing unimodular operations, unimodular row operations, right. This and many more is what we will see in the next few lectures. Till then, bye from my side, take care.